So second half of this video on entropy isn't going to be very long. We just got a few slides to finish up. So the stuff that we did previously, the fact that entropy has different microstates, and depending upon what kind of state the material is in and so forth, you have different numbers of microstates, therefore different entropies, leads us into the third law of thermodynamics, which basically says that the entropy of a pure crystalline substance at absolute zero is zero. So basically, at absolute zero, all motion stops. So if there is no motion, there is no possibility of microstates. So taken Boltzmann's idea, you've got S is equal to K times the natural log of the number of microstates. Well, at 0 degrees, everything's stuck in one position. There is only one snapshot you can take, so the natural log of 1 winds up being 0, and so the entropy overall winds up being 0. The entropy of a pure crystalline solid, again, is 0 at absolute 0. If you take a look at this graph, supports that idea. As we increase temperature, we start increasing the motion, so the number of microstates is starting to increase. What happens here? Why is this a vertical line here? Because remember that at the melting point, temperature's not changing, you're only absorbing energy in the form of potential energy, because we're breaking IMFAs at this point, likewise at the boiling point. So here's kind of a visual of entropy versus temperature, showing that as you increase temperature, you're increasing the number of microstates. So there are tables of standard entropies. No standard entropy is ever 0. Remember, we had some delta H's that were 0 if the substance was in its natural state. Enthalpy is 0 for something like O2. That is not the case with entropies, because standard entropies are measured at 298, which means you still have some motion going on. So nothing is 0 in terms of entropy at standard conditions. Standard entropies, just to give you some practical experience here, or practical logic, that's a good phrase. Standard entropies tend to increase with increasing molar mass. Why is that? Well, more molar mass means you've got probably more atoms, or at least bigger atoms, and so the chances of positions are going to increase with that. So you go from hydrogen gas, which is very small 2 atom, to something like benzene. Your microstates are increasing, which means your entropy is increasing. Liquids, gases, solids, notice what are happening to the numbers. Gases have a lot more entropy than liquids, than solids. So they increase with the number of atoms because of the number of possible microstates. They're also going to increase with the state. So we can figure out entropy changes for a reaction very similar to the way we figured out entropy changes, or enthalpy changes for a reaction. The change in entropy is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. So entropy is a positive. So if we're looking at the entropy of a product, that's a positive value. If we're looking at the entropy of a reactant, we're taking away that order, and so we've got to subtract the reactants from it. And then these values, N and M, just represent coefficients. So you're going to find standard entropies in a table, and remember that for pure elements, there is a value for the entropy, unlike for delta H, where there's no value, it's a 0. So here's an example. We want to determine the standard entropy of the reaction that you see here. I got these standard entropies right from Appendix C. Appendix C has delta H values. It also has delta S values, and it also has Gibbs free energy values, which we'll get to momentarily in our videos. So if these are all the numbers, what am I doing? I'm going to take the reactants, or I'm sorry, I'm going to take the products. Those are going to increase my entropy, so I'm going to keep those positive. I'm going to subtract the values of entropy for the reactants because I'm losing that disorder. So sum of the products minus the sum of the reactants. Again, you've got to consider the coefficients. So 2 aluminums times 3 waters minus the sum of 1 aluminum oxide and 3 hydrogen gases. We wind up with a delta S of positive 180.39 joules per Kelvin. So this is important leading up to subsequent conversations. Delta H used to always be kilojoules per mole. Delta S is joules per Kelvin, because remember it was Q divided by T for S. So joules per Kelvin, not kilojoules, joules. Make sure you pay attention to the units of your numbers here. And that should conclude what we need to talk about in terms of entropy at this point in time. We are going to use the idea of entropy, combine it with the idea of enthalpy into something called Gibbs free energy, which is what we overall use to determine spontaneity of reactions. So our next set of videos is going to be covering Gibbs free energy.